All right, so I'm finally able to go back and record the hydrates information, the lesson on hydrates. The microphone had died the other day and I wasn't able to record it during class, so I'm going back and recording it for you guys. So a hydrate is a compound it's an ionic compound that has water molecules chemically attached to it. So in your lab that you're going to be doing, you're going to be using a hydrate. Now a hydrate is a solid substance. I don't think I said that to my B-Day classes. A hydrate is a solid substance. The water's just kind of stuck in between the ionic compound, like stuck within the ionic crystal structure, okay? So, for example, CuSO4.5H2O, like we have here, all right? What that means is to the copper 2 sulfate, that's the name of it, copper 2 sulfate, already written there for you, to that copper 2 sulfate, like within it, there are 5 water molecules for every 1 copper 2 sulfate particle, okay? So when we name a hydrate, we name the ionic compound part like normal. So CuSO4 is copper 2 sulfate. You should already know that from Unit 4. Then to indicate that it is a hydrate, we're going to use the word hydrate, but then put the covalent prefix for the number of water molecules in front of the word hydrate. So since CuSO4.5H2O, there's 5 waters, so it's pentahydrate. Okay. So we'll do a couple more examples and then we'll do some math with this. So calcium sulfate dihydrate, calcium sulfate is CaSO4, and then it's dihydrate, so we're going to do a little dot, 2H2O. And then for BaCl2.9H2O, BaCl2 is barium chloride. And then 9, the prefix for 9 is nana, and then hydrate. So all together, it's barium chloride nanohydrate. All right, now, in the lab, you are going to heat up your hydrate, and that's going to cause the water molecules to leave the hydrated compound. You're actually breaking bonds there. It is a chemical reaction. It's not evaporation. I mean, the water will eventually evaporate because you're going to be heating it, but the original change is a decomposition reaction. You're going to be breaking the bond of the water molecule within the hydrate. All right, so it's not a physical change. So just keep that in mind. Now, before we can talk about the calculations that you're going to be doing in your lab, let's first talk about how we find percent composition of a hydrate. All right, so just keep in mind, when you're calculating the percent composition of a hydrated compound, you are going to calculate the percent of the ionic compound and the percent of water for each one. You are not going to separate it out into the individual elements like you did with regular percent composition. Hydrates are actually a little bit easier because you're only going to find 2 percentages. The process is the same though, where you first need to write the chemical formula, then calculate the entire molar mass, and then do your math, okay? So this one, lead 2 nitrate trihydrate. Lead 2 nitrate is PbNO3 2, and then trihydrate means that there are 3 water molecules attached, okay? So when calculating the entire molar mass for this substance, lead is 207.20 from the periodic table. We have 2 nitrogens in lead 2 nitrate. And then in lead 2 nitrate, we have 6 oxygens. Now, yes, we're using a dot, and in math, that dot means that we are multiplying, but with this, as a hydrate, we're just adding the 3 waters, okay? Well, in water, there are 2 hydrogen atoms, so we have 3 waters total, so 3 times 2 is 6, so we have 6 hydrogens, and we have 3 oxygens. that coefficient in front of the water distributes to both things. That is the most common mistake that people make on these problems, is they don't distribute the coefficient to the oxygen, and they only account for it with the hydrogen. So just be aware that that goes to everything. Just like when we were balancing it, it applies to everything. So I'm adding up all of these numbers to calculate the entire molar mass, and I got 385.28, and remember our units are grams per mole. So now I have the entire molar mass. This number here, the 385.28, is going to be my denominator in my 2% calculations. So we're going to find the percent of PbNO32 and then the percent of water. Like I just said, the denominator is going to be the same for both, and that's going to be the 385.28. The numerator is going to be the mass of those components. So for lead-2 nitrate, we have this portion here. That was the mass of lead-2 nitrate. So that's going to be my numerator on the percent of PbNO32. So I'm adding those back up. And I got 331.22. And then I'll multiply that by 100. And I'm getting 85.97% lead-2 nitrate. And then this portion here, oops, too far. This portion here is my numerator in the percent of water calculation. And that's 54.06. Divide and multiply by 100. And I'm getting 14.03% water. So those are my two answers for this problem. And then I can add up those two numbers just to confirm that they add up to 100 or close to it, and they do. Okay, remember, use that as a final check to make sure you've done the problem correctly. All right, now going a little bit further with this, just like we did with regular percent composition, we can calculate the mass of the individual components depending upon what the percent is. And I had actually changed this to be 40.0 grams in your packet. Like, you already have it right. I changed it. I just forgot to change it on my flip chart. So we have a 40-gram sample of this entire hydrate, the lead-2 nitrate trihydrate. We want to know what is the mass of water present. Okay? So remember, you can set this up like a proportion, or you can multiply the percent by the mass. It doesn't matter, as long as you do the math and you show your work. So we had previously calculated in number 1 that we had 14.03% water in this entire compound. All right? So if we set it up like a proportion, we want to know what is the mass of water, so X, in 40 grams of this substance, knowing that 14.03% of it is water. So part over whole, 14.03 over the total 100% equals X over 40. And again, if the units throw you off, get rid of them, and then you just have X over 40 equals 14.03 over 100. To solve for that X, you're going to cross multiply. So you have X times 100 equals 14.03 times 40. And then you're going to divide. So you're going to multiply 14.03 by 40 and then divide by 100. At this point, it's just algebra. But we do need to account for sig figs because this is science, and science has uncertainty in the measurement. So we always look back at our measured value, 40.0 grams, and that has 3 sig figs, so our answer needs to have 3 sig figs. So 14.03 times 40 divided by 100, rounded to 3 significant figures, is 5.61, and our units are grams of water. So in this entire 40-gram sample, we're going to have only 5.61 grams of water. The remaining mass will be the lead to nitrate. Okay. And then on your own, go ahead and calculate the percent composition for this second hydrate and do the mass depending upon, find the mass of each ionic compound and water. Do 3 and 5. I had a typo. I forgot number 4. Sorry about that. So you can do that on your own. If you were here in class, you've already done that and we went over it, but do that as extra practice. Okay? And that's what hydrates are. I've already recorded the video, or I will be recording the video on how to determine empirical formula of a hydrate. So that will help you for your lab calculations once we do it.